You know, it's almost easy to forget just how revolutionary recent progress in language processing has really been.
Hmm.
I mean, just a few years back, machine translation, it was often pretty clumsy, right?
Oh, definitely. Sometimes barely usable.
But the speed now, the speed these systems learn and the quality they get, it's genuinely astonishing.
It really is. And, if you're someone who really values getting to the heart of these big advancements quickly.
Yeah, maybe you're prepping for a meeting or just curious.
Exactly. Or trying to grasp the cutting edge in a field, then this deep dive should be right up your alley.
Absolutely. So today, we're diving into a real landmark piece of research. It's the paper, Attention is All You Need, came out of Google Brain, University of Toronto. A few key places.
That's the one. And it introduced a completely new way, really, of building neural networks for language tasks. They called it the transformer.
Transformer. Oh,
And our goal today, really, is to pull out the core ideas behind this transformer model. We want to understand why it was such a paradigm shift for what we call sequence transduction tasks.
sequence transduction,
Yeah,
like translation, summaries.
precisely. Translating languages, summarizing text, even generating computer code. Anything where you're turning one sequence into another. And we'll unpack this without getting totally bogged down in the, super technical weeds.
Right. The aim is a clear takeaway understanding of this, well, pretty fundamental technology now.
Exactly. Give you that shortcut to understanding.
Okay. So what are we working with? We've got the original research paper itself, obviously.
Yep. The paper lays out the architecture, the experiments.
And I see it also has some helpful diagrams, those figures showing how the pieces fit together.
Yeah, figure 1 and 2 are particularly useful for visualizing the structure and the attention mechanism itself. They really help.
Great. Okay. Let's dive in then. Before the transformer arrived on the scene, what were the main ways people tackled these sequence problems?
So the dominant approaches, they were largely based on things like recurrent neural networks, RNNs.
RNNs, right? LSTMs, GRUs, that kind of.
Exactly. And also, to some extent, convolutional neural networks, CNNs. These models often use what's called an encoder-decoder structure.
Okay.
And the really successful ones, especially in the few years before this paper, often added attention mechanisms on top to sort of help the encoder and decoder parts talk to each other effectively.
Right. Attention wasn't totally new with the transformer, but it played a different role before.
Correct. It was often an enhancement, not the core mechanism.
So what were the big limitations then? What wasn't working well enough with those RNNs and CNNs that made people look for something totally new?
Well, a primary bottleneck, especially with RNNs, was their sequential nature. They process information step by step, word by word, basically.
Following the order of the sentence.
Precisely. And that makes it really hard to parallelize the training. You can't process the end of the sentence until you've processed the beginning.
Ah, okay. So training takes a long time, especially for long sentences or documents.
Exactly. And memory limits also played a role, restricting how much you could process in one go. People developed clever tricks like LSTMs and GRUs to help manage information flow over time, but that fundamental sequential constraint, it was still there.
That makes sense. One step at a time just sounds slow when you've got massive data sets. What about the CNN approach? We know they're great for parallel processing in, like, images.
That's true, yeah. And models like ByteNet or ConvS2S did use CNNs. They could process different parts of the input or output sequence in parallel.
Okay, so potentially faster.
Potentially, yes. But the challenge for CNNs was often learning long-range dependencies.
Meaning how a word early in a sentence affects a word much later on.
Exactly. In these convolutional models, relating two distant positions required more computational steps. The number of steps grew, either linearly or logarithmically with the distance.
So the further apart the words, the harder it was for the CNN to connect them directly.
Kind of, yeah. It took more layers or wider convolutions. It wasn't impossible, but it was less direct than you might want.
Okay, so RNNs were slow because they were sequential, and both RNNs and CNNs struggled a bit with these long-distance relationships in the sequence.
That's a fair summary, yeah.
So where did attention fit in before this paper? You said it was used as an add-on.
Right. Attention mechanisms were already known and valued. They let a model, say the decoder part, directly look back at different parts of the input sequence and decide which parts were most important for generating the next word.
Regardless of how far back that important word was.
Exactly. Regardless of distance, it was powerful and used successfully in machine translation and other tasks, often alongside an RNN.
But the big leap, the core idea of attention is all you need, was to just ditch the RNN and CNN parts altogether.
Precisely. That was the radical idea. They basically said, what if we rely only on attention mechanisms to figure out all these relationships, both short range and long range?
Just attention, doing all the work.
Just attention. And because attention can look at any part of the sequence directly, it allows for massive parallelization during training. And as it turned out, it also got much better results.
Okay, wow. So let's get into this new design then. You mentioned the encoder-decoder structure was still used, that basic framework.
Yes, the transformer keeps that general encoder-decoder framework. It's a common pattern. The encoder takes the input sequence, say our English sentence, and maps it to a sequence of continuous representations. Think of them as like rich, context-aware embeddings.
Capturing the meaning.
Right. Then the decoder takes that sequence of representations from the encoder and generates the output sequence, the German translation, maybe one element at a time.
One element at a time. That sounds sequential still.
Good point. The output generation is sequential, or autoregressive, as they call it. When predicting the next word, the decoder considers the encoder's output and the words it has already generated itself.
Okay, got it. The generation is step by step, but the internal processing can be parallel.
Exactly. And how does the transformer implement this? Well, Figure 1 shows it clearly. Both the encoder and decoder are made up of a stack of identical layers.
Stacks. How many layers are we talking?
In the base model discussed in the paper, they used n equals 6 layers. So 6 layers in the encoder stack, 6 in the decoder stack.
Okay, 6 on each side. Let's zoom in on the encoder first. What's inside one of those 6 encoder layers?
Each encoder layer has 2 main parts, 2 sublayers.
Okay.
The first is a multi-head self-attention mechanism. We'll need to unpack that. The second is a simple, position-wise, fully connected feed-forward network.
Multi-head self-attention and a feed-forward network. Let's start with self-attention. What does that mean?
So self-attention means the attention mechanism is looking at relationships within the same sequence. The queries, keys, and values, the components of the attention calculation, they all come from the output of the previous layer in the encoder.
So each word is looking at all the other words in the same sentence, or representation of the sentence.
Exactly. To figure out how relevant they are to its own meaning and context, it's like each word asks, how important is every other word here for understanding me right now?
Okay, that's powerful. It gets context from the whole sequence directly. And the second sublayer, the feed-forward network.
Right. After the self-attention does its thing, the output goes through a standard feed-forward network. But importantly, this network is applied to each position independently and identically.
So the same network processes each word's representation separately.
Yep. It sort of processes the information gathered by the self-attention for each position.
And I remember reading about residual connections and layer normalization, where they fit in.
Ah, yes. Crucial for making deep networks trainable. Around each of these 2 sublayers, the self-attention and the feed-forward network, they use a residual connection.
Like a shortcut, adding the input of the sublayer to its output.
Exactly. So it's X plus sublayer, X.
Yeah.
And then they apply layer normalization to that sum. Layer norm, X plus sublayer X.
Okay, and that helps with gradients, stability.
Yeah, helps stabilize the learning, prevents gradients from vanishing or exploding, and just generally makes it possible to train these deeper stacks of layers effectively.
Got it. So the encoder layers use self-attention to relate words within the input, process each word individually, and use these residuals and normalization tricks to keep things stable.
Now, what about the decoder? Similar idea.
Very similar structure, yes. The decoder is also a stack of N6 identical layers, and each layer also has that self-attention mechanism and the position-wise feed-forward network, again with residuals and layer norm.
Okay. But it must be different somehow, right? It needs to produce the output translation.
Right. There are 2 key differences in the decoder layers. First, there's the third sublayer inserted between the self-attention and the feed-forward network.
A third one, what does that do?
This third sublayer performs multi-head attention, but critically, it takes queries from the decoder's previous layer, and the keys and values come from the output of the encoder stack. So that's the connection. That's how the decoder pays attention to the input sentence representation that the encoder created.
Precisely. It allows every position in the decoder to attend over all positions in the input sequence. That's vital for translation, obviously.
Makes perfect sense. And the second difference, you mentioned masking earlier.
Yes. The self-attention sub-layer in the decoder, the one looking at the decoder's own sequence, is modified. It uses what they call masked multi-head self-attention.
Masked. What's it hiding?
It's masking out or preventing attention to subsequent positions in the decoder's input. So, When the decoder is trying to predict the word at position I, it's only allowed to attend to positions less than I the words it has already generated.
Okay. Why is that necessary?
It preserves the autoregressive property.
Hmm.
Remember, the decoder generates the output one word at a time, left to right. It shouldn't be allowed to cheat by looking at the future words it's supposed to be predicting.
Ah, of course. It needs to predict the next word based only on the input and the words it's already outputted. The masking enforces that.
Exactly. Combine that masking with shifting the target output embeddings one position to the right during training, and you ensure the predictions for position I only depend on outputs up to I1.
Okay, that clarifies the decoder structure. Now let's dig into the core mechanism itself, this attention. The paper talks about scaled dot product attention. Can you break that down? Figure 2 seems key here.
Absolutely. Scaled dot product attention is the fundamental building block. Think of it as a function. It takes three inputs, a query, Q, and a set of keys, K and values V.
Query keys, values, okay.
The goal is to compute an output which is essentially a weighted sum of the values.
Yeah.
And the weight given to each value depends on how well its corresponding key matches the query.
How well the key matches the query. How's that measured?
It's calculated using a dot product. You take the dot product of the query with each key. Simple, fast matrix multiplication in practice.
Dot product gives a similarity score, kind of.
Yeah, compatibility score. Then these scores are scaled down. They're divided by the square root of the dimension of the keys, which they call dt.
Scaling. Why the scaling?
Good question. They hypothesize that for large values of dk, the dot products might grow really large in magnitude.
Okay.
And if those dot products get too large, feeding them into the next step, the softmax function.
So softmax turns scores into probabilities, right?
Yeah.
Summing to 1.
Exactly. But if the inputs are huge, the softmax can saturate. It pushes the probabilities towards 0 or 1, and the gradients become incredibly tiny.
Making it harder to learn.
Very hard. So scaling by 1 over the square root of dk helps keep those dot products in a reasonable range, preventing the gradients from vanishing during training. It's a practical stabilization trick.
Makes sense. So dot product scale, then softmax to get the weights.
Right. The softmax gives you the weights, and then you multiply those weights by the corresponding values and sum everything up. That weighted sum is the output of the scaled dot product attention. Equation 1 shows the neat matrix form for doing this efficiently on batches.
Okay, that's the basic attention. But then they use multi-head attention. Why multiple heads? What does that add?
Right, multi-head attention, also in figure 2. Instead of just doing that scaled dot product attention once with the full dimensional keys, values, and queries, they first project the queries, keys, and values into lower dimensional subspaces. They do this H different times using different learned linear projections for each head.
So multiple smaller attention calculations happening at once.
Exactly. You run the scaled dot product attention function in parallel for each of these H projected versions. This gives you H different output vectors.
Okay, like getting multiple perspectives on the relationships.
That's a great analogy. Each head can potentially learn to focus on different aspects of the relationships or different representation subspaces. Maybe one head focuses on syntactic links, another on semantic similarity,
Interesting. So you get these H outputs. Then what?
Then they simply concatenate all those H output vectors back together. And finally, they apply one more linear projection to this big concatenated vector to get the final output of the multi-head attention layer.
So project down, run attention in parallel heads, concatenate, project back up.
That's the essence of it. The paper uses eight heads, and they set the dimension of each head, dk and dv, to be d model, so phi 128 equals 64. This means the total computation is similar to a single head with the full dimension, but you get the benefit of these diverse perspectives.
Allows the model to jointly attend to information from different representation subspaces at different positions, as the paper puts it.
Precisely. It prevents averaging out potentially distinct types of useful information that a single attention mechanism might struggle to capture simultaneously.
Okay, this picture is getting much clearer. We have the encoder-decoder stack, layers with multi-head attention, self-attention, and encoder attention, feed-forward nets, residuals. But wait, we threw out the RNNs and CNNs? How does the model know the order of the words? Isn't that crucial?
Excellent point. Absolutely crucial. Since the model itself just using attention doesn't inherently process things sequentially like an RNN or have a local receptive field like a CNN, it has no built-in sense of word order.
It would just see a bag of words, essentially.
Pretty much, yeah. If you just fed the word embeddings in, the cat sat and set the cat might look the same to the attention mechanism alone.
So how did they fix that?
They introduced positional encodings. These are vectors that are added directly to the input embeddings at the bottom of both the encoder and decoder stacks.
Added to the embeddings, so combining word meaning with position info.
Exactly. These positional encoding vectors have the same dimension as the embeddings D model, so you can just sum them up. It injects information about the position of each token within the sequence.
Okay, what do these positional encoding vectors look like? How are they generated?
The paper proposed using sine and cosine functions of different frequencies. They provide specific formulas. Basically, for each position pulse in the sequence and each dimension of the embedding, they calculate a value using sin-pulse 1000 toy Z2ID model, or cos-pulse 1000 2ID model.
Whoa, okay. Sine and cosine waves. Why that specific approach?
The idea is that these sinusoidal functions create unique positional signatures. And crucially, they hypothesized it would allow the model to easily learn relative positions. Because for any fixed offset k, the positional encoding at post plus k can be represented as a linear transformation of the encoding at post.
Ah, so the model could learn what does 3 words ahead look like relative to any position.
That's the intuition. Interestingly, they also tried learning the positional embeddings instead of using this fixed sinusoidal function. They found it worked almost identically well, but they stuck with the sinusoidal version, partly because they thought it might generalize better to sequence lengths longer than those seen during training.
Okay, so positional encoding solved the order problem by adding time signals to the embeddings. Now, the paper really hammers home why self-attention is superior to the older methods. Can we summarize those key advantages again? Table 1 seemed important there.
Definitely. Table 1 gives a great comparison. There are 3 main advantages they highlight.
Okay, number 1.
Computational complexity per layer. Self-attention layers are actually faster than recurrent layers when the sequence length n is smaller than the representation dimension d.
Which happens often in translation with things like word pieces.
Exactly. So faster computation per layer in many practical cases.
The advantage too.
Parallelization. This is a big
Okay.
one. Because self-attention can compute relationships between all pairs of words simultaneously, the amount of computation that must be sequential is constant O1 operations.
Whereas RNNs are O and sequential steps.
Right. So self-attention allows for way more parallel computation on modern hardware like GPUs or TPUs.
Yeah.
This massively speeds up training. We're talking orders of magnitude faster training times possible.
Huge practical impact. Okay, third advantage.
Path length for long-range dependencies.
Yeah.
This is maybe the most theoretically compelling one. In a self-attention layer, the maximum path length between any 2 positions in the sequence is constant O1.
Meaning any word can directly attend to any other word in one step.
Exactly. Compare that to an RNN where the signal has to travel step by step, so the path length is OENE, or even CNNs where it's logarithmic O log capital N, or linear OEZ, depending on the structure.
So learning connections between distant words is just fundamentally easier for self-attention.
Much easier. The model architecture doesn't inherently make it harder just because words are far apart. They also mention, though, that for extremely long sequences, you might use restricted self-attention, only looking at a neighborhood to manage compute costs.
Makes sense. And they touch on interpretability, too,
Mhm.
looking at the attention weights.
Yeah, briefly. The appendix has figures showing that the attention heads seem to learn to pay attention to syntactically or semantically relevant parts of the sentence, which can offer some insight into what the model is doing.
Okay, so faster, more parallelizable, better at long-range dependencies. That sounds like a winning combination. How did it actually perform on real tasks? The machine translation results look pretty striking.
They really were. Table 2 shows the results on the standard WMT 2014 benchmarks. On English to German translation, their transformer, big model, got a BLEU score of 28.4.
And how good is that?
That was state-of-the-art by a huge margin at the time. Over 2 full BLEU points better than any previous model, including complex ensembles of multiple models.
Wow, a single model beating ensembles by that much.
Yes. And perhaps even more impressively, they achieved this with way less training cost. The big model trained for just 3.5 days on 8 P100 GPUs. Previous state-of-the-art models often trained for much longer on more hardware.
Faster training and better results.
Exactly. Even their smaller transformer-based model outperformed previous bests with less training effort. Similar story on English to French. The big model set a new single-model state-of-the-art BLEU score of 41.8, again, trained much more efficiently.
That's really convincing evidence. But was it just good at translation, or could it handle other things too? They mentioned constituency parsing.
Right. They wanted to show it wasn't just a one-trick pony. They applied it to English constituency parsing, basically figuring out the grammatical phrase structure of a sentence.
That sounds quite different from translation. More structured output.
Yes, very different. Longer outputs, strong structural constraints. And RNN-based sequence-to-sequence models hadn't historically done super well on that task, especially with limited data.
And the transformer.
Even a relatively small 4-layer transformer trained on just the standard Wall Street Journal section of the Pentry Bank, about 40,000 sentences, performed really well, better than the standard Berkeley parser baseline.
Even with limited data.
And when they used semi-supervised learning, leveraging a much larger unlabeled data set, it performed even better, surpassing previous RNN-based results, particularly in low data settings. It showed the architecture could learn these complex structural relationships effectively.
So it demonstrated real versatility beyond just translation.
Definitely. It suggested this attention-based approach was broadly applicable to sequence modeling problems.
Okay, so just to sort of wrap up the core ideas for everyone listening, we have this transformer architecture. It completely ditches the recurrent or convolutional layers that used to dominate.
Right. No more step-by-step RNN processing.
Instead, it relies entirely on attention mechanisms, specifically this multi-head self-attention.
Letting every element in a sequence look directly at every other element.
And that gives it major advantages.
Yeah.
It's much faster to train because it's highly parallelizable.
Yep, huge speed-ups.
It's inherently better at learning long-range dependencies because the path length is constant.
Path length, a key theoretical advantage.
And this led to breakthrough results in machine translation, better scores, less training time, and showed it could generalize to other complex tasks like parsing sentence structure.
That sums it up perfectly. The core shift was making attention the central, really the only, mechanism for relating positions in a sequence, both within the input and between input and output.
It really feels like one of those aha moments in research, doesn't it? Taking something that was maybe seen as secondary, like attention, and realizing it could do the whole job and do it better.
Absolutely. Moving away from the sequential assumption of RNNs was a major conceptual leap with enormous practical consequences.
And for you, listening in, trying to get up to speed efficiently, understanding this transformer concept is just so crucial because it really underpins so many of the advanced AI language tools we see today, from translation to chatbots to code generation.
It's foundational now, which actually leads to a kind of interesting thought to leave you with.
Oh, yeah.
Well, now that you understand how powerful attention is for processing language sequences, how might that same principle apply elsewhere? Think about other kinds of complex sequential data.
Like stock market data, or maybe protein sequences in biology.
Exactly. Financial time series, biological sequences, maybe even analyzing music or video. Could these seemingly sequential processes also be reimagined through this lens of parallel attention? What hidden long-range dependencies might that uncover?
That's a really interesting question. Thinking beyond language to other sequences. Definitely food for thought.
And of course, if you do want to get into the nitty-gritty, the original paper, Attention is All You Need, is out there. And the code is often available too.
Right. So for those wanting the deepest dive, the source material awaits. Great resources to explore further if this sparked your interest.